Alright students, I'm just going to zip through the start of the next chapter. This might be the last chapter we do before the end of the year. I don't know, but at the moment we've got 2 weeks to go through this. With me, I'm not sure what you're going to be doing with this, apart from probably finishing off sequences and series or whatever. I'm not sure. Maybe doing some revision on mechanics. Who knows? Anyway, we're going to look at Radians. So, Radians are a unit of measure for angles. There you go. That's the whole chapter done. That's all you need to know. But of course it's not. Um, Radians are a unit of measurement for angles. So up until now, you'll have measured all of your angles in degrees. So you might have, I've done this. This is clearly disproportionate, like not correct here. But you might have here, let's say a wedge in a circle. This is 1 degree, and then that means you can fit 360 of those into a circle. That's obviously a little bit bigger than 1 degree, but you know, that's all I could do drawing wise. And when you think about this, you kind of realise this is a bit odd. Who picked this random 360 number? What's that about? Where does that come from? And the answer is not actually a particularly concrete one. There's a few possible potential reasons for it that you can look up. It might be just because it's vaguely similar to the amount of days in a year, or to do with the way that people would bisect equilateral triangles into circles. I don't really know. There's kind of not a concretely known answer to that. It's a bit odd, and a thing that kind of makes a little bit more sense is actually if we think of our measurement of a thing being like this. So what I might think is, well, if this is a circle that I have here on the right hand side, so let's make a note of that. 1 degree, 360 in a circle. There we go. So if I have a circle like this, and I make a kind of pizza wedge on it, and what I'm going to do is I'm going to say, well, that pizza wedge has got side lengths r, like that, because that's the radius of the circle. And I'm going to pick the size of this pizza wedge so that the arc length is also r. So it has a length of radius here, and then we also have this arc length going around here, which is the same length as the radius. And this is how we define 1 radian. So in here, in this wedge, where the arc length is the same as the radius of the circle, here we have 1 radian. Like that. And we can kind of immediately think why this might be a quite nice way to measure the size of an angle, because what I might want to think about is, well, how many times will a radian fit into a circle? And if I'm saying that, what I'm essentially saying is, well, how many of these wedges here can I fit? If I stack them inside the circle, how many would go in there? And the answer is very nice, actually, because we can answer the question by also thinking, well, how many of these arc lengths, these r-long arc lengths, can I fit into the circumference? And you might have spotted what's going on here, because essentially I'm saying, how many times can I fit the radius on the circumference? And we know that the formula for the radius, the circumference of a circle, the circumference is equal to 2 pi times the radius. So this full distance around the outside of the circle is equal to 2 pi amounts of this length r. So we can actually say that by following this logic, there must be 2 pi radians in a circle or a full rotation. So in the same way that I could fit 360 of these wedges on the left into this circle, I can fit 2 pi of these wedges on the right into this circle. So it's like 6.2-ish of these wedges inside a circle. And this is obviously not drawn to scale. So there's 2 pi radians in a circle. And that leads us to saying, well, if we're thinking about converting between radians and degrees, because they're just a measurement of, a size. So like I might convert between miles and kilometers or meters and centimeters or whatever. I want to know what the multiple is that converts them. Well, 360 degrees is equal to 2 pi radians. And I'm just going to write 2 pi rad like that. So this is kind of like an important note that you definitely need. 360 degrees is equal to 2 pi radians. And we actually often don't write units for radians. So like in degrees, we have this little circle up here. For radians, you might write 2 pi rad, or you might actually write 2 pi and then a little c up like that. So for some reason, I don't know why that is. But usually, actually, because we write radians and because of the way this works, we'll see soon, they actually often end up being multiples of pi. If we don't write a unit, we kind of just assume, well, we talk about radians. What's the point? Well, the first point is it actually makes logical sense. Like this makes logical sense that it would be related to the amount of times you can fit the radius into a circle. That's how we've been working for probably years now, working out the circumference of a circle. So it's logical that that kind of works. There's other reasons as well, actually. And soon, by soon I mean September, hopefully we're back in school by then, we're going to start thinking about calculus again. So i.e. differentiation and integration. And we might want to start thinking about, well, if I say that y is equal to sine x, what happens if I differentiate that? And the answer is, you actually get cos x if you differentiate sine x. It's just a fact. We can prove it a number of ways, which I won't do now, but that's just something that you're going to learn later. So if you differentiate sine x, you get cos x. And this relationship here only works in radians. So if we work in degrees, we cannot do calculus, so differentiation or integration, involving a trigonometric function. So radians, very, very important. Degrees aren't going to be gone forever. So, we don't have to completely forget everything we know about degrees. You're still going to get questions in degrees. Quite a lot of mechanics questions often still involve degrees because, that's just what people work in. But we are going to use radians a lot now, and you need to look out for in questions whether they're using radians or they are using degrees. So, what do we do if we have a question where we need to go between one or the other, or a situation? I mean, this is kind of a bit of year 7 maths, basically. If I go back to the first page, 360 degrees is 2 pi radians. Well, it's actually even more useful to just say 180 degrees is 1 pi radians. So we just need to think, and you've probably seen little diagrams like this before, like, flow charts with like multiplying times 10 times 100, whatever, to go between centimeters and meters and so on. What do we do to work it out? Well, if I want to go from 180 and turn it into pi, I can divide it by 180, because 180 divided by 180 would be 1, and then times it by pi. Likewise, the opposite direction, I can divide it by pi and times it by 180. And that's kind of just like a little formula that will take you between the two. So this is converting from degrees to radians, because we know the equivalence, the kind of important equivalence we can use to compare them is the fact that 180 is equal to pi. In most cases though, it's actually easier to just kind of think about what the the angle in question is, and then just convert it. Because we can just think like, well, if I wanted to know what is 90 degrees in radians, if we just look at this original statement that 180 is equal to pi, it makes sense that 90 degrees is actually equal to just pi over 2 radians. So I would just write, oh, it's just pi over 2. 45 degrees, well, following on from before, it must be pi over 4. So say I could also say, well, 45 divided by 180 times it by pi, that's the answer I would get. But, I mean, come on, we're not going to do that. 135 degrees, I mean, there's a few ways you could think about this. You could do the conversion, or you can actually just think, well, 135 is 90 and 45 together, so we can add these two up. All of your kind of logical skills that you use. Okay, you have all the faculties to do this. It's 3 over 4 pi. 72 degrees, kind of a nice one. Like, maybe you look at this one and think, oh, I need to do the full kind of conversion for this because it doesn't seem like it's a particularly nice fraction of 180. 72 is actually 2/5 of 180 because it's 36 times 2. So 2/5 pi. I can just say, well, if I couldn't work that out, I do 72, I divide it by 180, I times it by pi. But 72 divided by 180 is going to give you 2/5, so it's 2/5 times pi. And we often would write our answers in terms of pi like this. So it's quite nice and tidy. That's cool. This is in exact form. Pi over 3. Well, again, I can just look, well, what happens if I divide this by 3? It must be 60 degrees. Pi over 3 radians is 60 degrees. Pi over 6, same logic. Divide it by 6, it's 30 degrees. 3 pi over 2, well, half of 180 is 90. Times it by 3, it's 270. So it's 270 degrees. And then 5 pi over 6, divide 180 by 6, then times it by 5. It's going to be 150 degrees. You can see, hopefully you're keeping up with my logic for working these out. I'm kind of, rather than using this kind of conversion method of divide by 180 and times it by pi and do all that sort of stuff, really what I'm doing is just looking at this equivalent statement, 180 equals pi, and then kind of multiplying and dividing both sides until I've got what I want. It's quite a good way to think about it. Common angles, just seen a few of these. These are angles in degrees that you would probably know from you probably know these from GCSE. And if I said like what's sine 30, you'd probably be able to tell it to me, or cos 30, at least I hope you'd be able to tell it to me. These are ones that you probably just want to kind of know off the top of your head. What are these in radians? Okay, so maybe what you want to do, pause the video right now, try and write in radians, what will all of these be as quickly as you can. Maybe with no working out. So pause it now, have a go at that. Okay, now unpause it. I'm going to quickly zip through what they are. 30 degrees is pi over 6. The 45 degrees is pi over 2. Pi over 2? It's not pi over 2, it's pi over 4. God, blimey. Still on half term in the brain. There we go. 60 degrees is pi over 3. 90 degrees is pi over 2. Because 180 degrees is pi. 120 degrees is 2 pi over 3 because it's 2 times the 60, so 2 pi over 3. 135 degrees, we saw that one already, it's 3/4 pi, and 270 degrees is 3 over 2 pi. So that's the exact same ones we worked out on the previous page. Graphs. So there's going to be a lot of occasions where we have to sketch graphs. So if I'm doing here, this is going to be the graph of y equals sine x in radians. So in radians, nothing is going to change about this graph except for the scale. And the vertical scale is also not going to change. The graph is still going to be between 1 and -1. So what we're really looking at is what are the key points that we would mark on the x-axis. So here, 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 and here. And that's going to give us a nice sketch of the graph of sine x. So it's just a change in scale on the x-axis. And if you want, you can go on Desmos, do graph of sine x, and then click on the settings, change it between degrees and radians, and see what happens. All we're going to do is we're just going to think, well, what does this graph normally look like in degrees? Well, let's say like the point on the very far right, this point here, is 360. But we're doing this in radians, so now it's actually 2 pi. We've actually stretched it down to be 2 pi. Similarly, with the middle point, it's normally 180. So now it's going to be pi, because that's what it is in radians. And then we just fill in the rest of it. So this is a halfway point, so this must be pi over 2. And 270 degrees is 3 pi over 4, or 3/4 pi, whatever. Okay, so that's all you need to do to sketch this in radians. I'm going to tell you that because that number looks really stupid. So let's just write it as 3/4 pi like that. Here's cos, same thing, 0, 1, and then at the bottom here we're going to have a -1, key points here, 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 and here, where 360 would normally be, 2 pi, pi, 3/4 pi, and a half pi there. Because this is normally 90, 180, 270, 360 going across. So these graphs are exactly the same. It's just that the scale has changed on the x-axis. They've been kind of stretched into radian mode rather than degree mode. Exact values. So this should be hopefully pretty familiar to you from GCSE maths. So you need to be able to find some exact values. This is a bit funny now in A-level maths because you can pretty much do all this in your calculator and it isn't often that it comes up, but you do get some kind of interesting trig proofs and stuff like that that might require you to do some exact values or some manipulation or something. So particularly the second little part of this, talking about sine x and equivalent angles, is quite important. Like, you should just kind of know all this stuff. If you look in the textbook on page, what page is it? Page 117. It's got a list of all the kind of classic exact values there. And that's exactly the same as the ones that you will know in degrees. It's just they're in radians now. So that's why I've written sine pi over 6 is a half, cos pi over 6 is root 3 over 2, because these are like sine and cos of 30. So it's the same output, etc. So this is important. You should know this from your year 1 trig. The way that we find other solutions for trigonometric equations. So this is totally equivalent to the way that we would do these in degrees. So like sine x is sine pi minus x is the same thing as saying sine x is equal to sine of 180 minus x. It's just this is in radians. So if it's in radians, to find the other solutions, like we would normally do, cos x is cos 360 minus x. To find the other solutions, we simply just use pi instead of 180, or 2 pi instead of 360. Sine and cos repeat every 2 pi instead of 360 degrees, whereas tan repeats every pi instead of 180 degrees now. It's exactly the same method as before, and this is going to be useful when you answer equations. You solve equations involve radians. But anyway, you might get a question like this one. Find the exact value of this. And you might ask, what the hell is the point of this? I can do this in my calculator, which you can, but I'm not going to show you how to do that for the minute. I'm just going to say, what if we didn't want to do it in our calculator? What if we wanted to do a little bit of mental maths and work it out from here? Because this can be a really useful skill if you're trying to unpick a piece of algebra or something complicated a bit later on. So, cos of 4 pi over 3. We're going to work with this for a little bit and see if we can come to some sort of a solution. So cos of 4 pi over 3 is equal to cos of 2 pi minus 4 pi over 3. And you're going to have to do a lot of fractions that involve pi when you do radians. The best thing to do is really just ignore the pi and put it back afterwards. This is just like saying, what's 2 minus 4 over 3? Well, 2 minus 4 over 3 is 2/3. And then we just do pi next to it, put the pi back. So it's cos of 2 pi over 3. So what is cos of 2 pi over 3? There's a couple of things you can do here. Some of you might prefer to say, okay, I'm just going to say, well, I know that this is actually cos of 120 degrees. Put it into degrees and then maybe you just know the answer. Or you could kind of just carry on in radians and try and work it out from there. I don't know. Okay. So there's a few things that we can do, but really I think to kind of get the solution to this one, we do want to have a quick look at the cosine graph, and we want to think about, well, where is this? This is actually a kind of a tricky one to find the answer for. So 2 pi over 3, or 120 degrees, okay, where is that going to be on my cos graph? It's actually going to be about here-ish. So that is going to be where my 2 pi over 3 is. So what I'm actually looking for is, what is this? And that y value is going to be the answer. And by symmetry, we can actually say, well, it must be the same as the y value up here, but minus it, because this distance here and this distance here, despite my inaccurate drawing, are going to be equal. Okay, so we need to think, well, if we know what is the on the left here, what is this value? And if this is pi over 2 and this is 2 pi over 3, you can just do a little bit of arithmetic to work out that this is actually going to be 1 pi over 3, like that. Okay, and similarly I could say, well, in the degrees, it might make it easier for us to spot this. This would be 90, this would be 120, you've got a distance of 30, so this must be 60. Okay, and 60 is pi over 3 in radians. So cos of 2 pi over 3, well, we know what cos of pi over 3 is. Cos of pi over 3 is, wait for you to work it out, cos of pi over 3 is a half. Again, even though it really doesn't look like it on my diagram, because my diagram is awful. It looks a little bit more like it might be on the bottom. Poor diagram drawing. Okay, so this cos of 2 pi over 3 is actually going to be equal to minus cos of 1 pi over 3. So it's going to be minus a half. Some people find these sorts of questions easier to do in degrees, so just convert it and do it. Honestly, this is good practice. I mean, you can do this all on your calculator as well to like check your answers. It can be useful to know how to manipulate these things, but it's not necessarily explicitly useful to be able to find exact values of cos of 4 pi over 3 um, with no calculator. You will have one with you, but it's still like a nice skill to know. And manipulating and looking at the graphs is important as well. You can use the cast diagram if you use that, but I personally don't actually even know how to use that, so awkward. Minus 7 over 6 pi sine of. So sine of this. Let's do some manipulating. So I'm going to say this is a negative. Maybe the first thing I want to do is make it a positive, so I can add 2 pi to it. So sine of this is going to be equal to sine of minus 7 pi over 6 plus 2 pi. So again, I can kind of just ignore the pi, or you can just work it out in your calculator. It doesn't matter. Okay, but this is, I suppose, technically not supposed to be done on a calculator. 7 over 6 plus 2, so it's like saying 7 plus 12 minus 7, well, it's minus 7 over 6 plus 12 is minus 7, so it's 5 over 6. So I think it's going to be sine of 5 over 6 pi. Again, usually the most comfortable thing to do here is to think, do I know like what the degrees version of this is? Maybe you don't. Maybe it's easier to use this again. Oh look, sine x is equal to sine of pi minus x. So sine of pi minus 5 over 6 pi, which is sine of 1 pi over 6. And again, we can kind of think, what's that in degrees? Oh, it's 30. What's sine of 30? Sine of 30 is a half. There you go. This is obviously doable in your calculator. You now have to start paying close attention to what's going on your calculator, because you're going to lose marks. I guarantee at least one of you will end up doing it in the real exam as well. I'm almost 100% certain about that. I'd probably place money on it in a bet. I'd rather you didn't know, so I'm going to tell you now. This little d means that your calculator is in degrees. So if I do sine of pi over 6 like I just did now, it gives me some crazy answer. Okay, but I know that what I'm really doing there is sine of 30. What I'm trying to do is sine of 30, because pi over 6 in radians is equal to 30 degrees in degrees. So I'll just do that again because I did that quite quickly. So shift, set up, press 2, degrees, radians, or gradians. We don't use gradians in A-level maths. But radians, switch to that, and then you'll see sine pi over 6 is a half. So pay close attention to this little box. Put it in radians for if you're working in radians. Change it back into degrees if the question's in degrees, because it won't give you correct answers. Okay. Before Friday, you should look at exercises 5A and 5B. They're really quite light exercises, to be honest. So it's fairly chilled. I know you're supposed to be revising for the binomial test, and I know Miss is giving you a test this week as well. On Friday, I will put up another video on the next bit of radians, which is looking at, going to be what? Oh god, shapes. Craziness. How exciting. So more shapes. So, see you then.